everyone and welcome to new discussion. In this lecture we are going to discuss about raster data model, and we will also try to compare with vector, see and we will see that what are the advantages and disadvantages associated with both types of models. As you recall that when we have discussed the data in GIS, at that time I said that there are two basic types. One is spatial data, another one is non-spatial data. And in spatial data, I mentioned first the vector, three types of vector entities: point, line, polyline and polygon, and which we have discussed. We have also seen demonstration also. Topology part we have also discussed. And next spatial data was which I mentioned in that one was the raster data. So, raster data again having two types, so that we will also see and then try to compare with vector data. Now, as you know that raster data is a little simpler compared to what vector data is, and here you are having the basically rows and columns. So, mathematically if we look at this one as a two-dimensional matrix, and one thing also very important, like in matrix, that a number of rows and columns need not to be the same. That means if they are same, then we will have a squared matrix, and if these are different like rows and columns, then overall shape of our matrix is going to be rectangular. So, same with the raster data, that rows and columns need not to be the same. However, the cell which is the unit of a raster has to be always square in shape. No other shape is allowed in raster data, because each cell is representing a ground area, and both x and y of cell are also same. So, if I say that though unit is in square in shape, however, the overall shape of a raster can be either square or rectangular, but the unit has to be always square. This one has to remember, this is very fundamental and this plays very important role in later analysis and other things. As you also know that raster data is a continuous data. As you can also see here that one cell ends, another starts. So, if I take like this yellow cell here, then next adjacent cell is green cell, and there is no gap between these two. But if there are two polylines like this or like two contours, in between we do not have any information whatsoever. So, that is why we call vector data as a discontinuous data or discrete data, and whereas for raster data we call as a continuous data. One cell or one pixel ends, another starts. So, within that raster file, like here which you are seeing a two-dimensional matrix, each cell is having its own color or pattern, but basically it is a value, and that value is assigned certain pattern or color. So, overall in the view you see like this. So, the overall shape can be square or rectangular, like here it is a rectangular, but overall but the shape of a raster unit like here it always is square in shape. Both n, x, y dimensions will remain same, and this is very important from unit points of view, because the third type of spatial data which we are also going to discuss later on, and not in this lecture, maybe in next lecture, about the triangulated irregular network, in which the unit is always triangle of varying size and shapes. There are advantages having such kind of model, data model to represent the surface. When I say continuous data or representing a surface, the two best or rather all three models, vector, raster and TIN, can do it. But TIN and this vector being discontinuous or discrete, only we can use the isoheids or contour lines, but between two contours we do not have any information. But there is no information gap in case of raster and neither in case of TIN, as you would see later on when we will discuss about TIN. So, all three data models can represent a surface, especially like terrain surface or topography of a terrain, can be represented very well. But in case of vector, it would be discrete. In case of raster, it is continuous. Throughout your data file, you are having some information on another, and same would be in case of TIN also. So, this is another very important point related with it. As I have already mentioned that the unit have to be square in shape in case of raster. Various formats for image and data are available, depending sometimes the big software people have developed their own format, like ArcGIS having their own format which is called GRD, grid format, TIFF tagged information file format. This one is a very common format for image data, because raster is having two types, one is grid and image. So, for image format, TIFF tagged information file format, or in short we also write sometimes only TIF, because this was earlier in the MS-DOS systems. After the in the extension space, there were only 3 digits or 3 places were allowed, so that became still popular. Another file format, especially for image data, is very popular, is called GIF, Graphic Interchange File Format. Now, this format is used for animated files. So, whatever the files which you see, or some cartoon kind of thing on your internet or on your mobile through WhatsApp or other social media platforms, they use this GIF. And if you want to create, and there are tools available by which you can create a GIF file that would be animated file, whereas TIFF will not allow you to store animated files. Another file format very famous for raster data, especially the image data, is IRDAS Imagine or .img. .img is also very popular and compatible with many GIS and digital image processing software. So, not a problem, and there are tools available in all good softwares, or separate tools are also available, where you can change from one format to another. So, suppose if I want to change from TIFF to IRDAS Imagine, I can do it within IRDAS Imagine, I can do it in ArcGIS, or separate softwares are available where I can change from one format to another. But one important point I want to mention here, that transforming from one format to another, always it is not fully transparent. Transparent means that there might be introduction of some errors. So, one has to be very careful. Let me give you one example here. Like if I convert a file which is originally in TIFF to JPEG, that is JPG, or in short we call as JPEG. Now, this format, JPEG format, is a compression format, and therefore, it will change the quality or deteriorate the quality of a TIFF file permanently. So, by mistake, if I have deleted original TIFF file, I got converted into the JPEG, and later on I want to restore the quality of my image, then it becomes impossible. So, that is why I said this is the conversion from one format to another, one image format to another, or one grid format to another. And before you delete the original file, one has to be very careful about this, whether this transformation from one format to another is fully transparent or not. If it is not, then please do not delete the original file, because that may be a very valuable data for you. So, we have to keep this thing. Now, the raster data types, I have already mentioned two main types, your grid and image. Example, on the right side you are seeing the grid example, and a very common data, grid data which we use in GIS, and later on in the last 10-15 lectures we are going to have lot of discussion about digital elevation models and their derivatives, and we will be using the same digital elevation model as shown here. So, this is grid data, as you can see, it is continuous, and here In this case, in particular this example, number of rows and columns are not same, therefore the overall shape of my raster is rectangular in shape, but data is continuous. There is a question will come about the spatial resolution, and of course we will have more discussion on this, but as the dimension equivalent ground area, if it is very small, then we call as a high spatial resolution, and if a ground area coverage is large by one single cell, then we call as a coarse resolution, and this is a relative terms. For someone 10 meter may be high resolution, but for another person a 10 meter may be coarse resolution. So it depends on the work or project in which you are going to imply a particular resolution data. So for those who are working in a large area, say continental scale, even 100 meter resolution or 1 kilometer resolution may be sufficient for them. But if I am working in a 10 square kilometer watershed or a district, then maybe I require very high spatial resolution data. So this dimension of the cell, which is equivalent to ground area, and decides basically what is spatial resolution. We will have a complete separate discussion also on this. Now as you have seen in case of point data or in our previous discussion related with the demonstration of softwares, that each vector entity, whether it is a point, polyline or polygon, can have theoretically n number of attributes. But in case of raster, each cell can have only single attribute. That is the limitation. That is the limitation. Though it is continuous, the limitation is you cannot have multiple attributes associated with each cell. Only one value. So if it is a typical elevation model, that cell value would be elevation value. But if I have created a surface for say pollution, then that would have my pollutants concentration, a particular pollutant concentration. So in a typical digital elevation model, that value is elevation value. Now many times though we may have a surface which is representing pollution or any other thing, but still we call as digital elevation model. So do not get confused in that. This is a common term which is used for grid files which is representing surface in a continuous fashion. Another type of raster data is the image data, and this image data which you are seeing, two examples of images are here. Both are having rectangular shapes, though they can have also square shape, and one is a colored satellite aerial photographs, the left one, and the right one is your satellite image of very high resolution. As you can see that all details are available here, and almost these two images are having almost the same colors as you see in the real world also. Because of very narrow bands, it is possible now to get images almost in the real color. If we are not using infrared or other channels, then it is possible. So your raster grid will look like something like this, and your raster image may look like this. Both are raster. Here the cell, instead of calling cell, we call as a pixel, which is a short form of picture element. And the cell values, how they are stored in the system, are also little different, which we will discuss later. So the major difference between an image and grid is, though both are raster, and shape of raster model can be either rectangular or square. However, the units which we in case of image we call as a pixel, picture element, and whereas unit for a grid we call as a cell. So that when I say cell, whenever I say cell, I mean I am talking about a grid, and whenever I say pixel, I am talking about an image. So that is why these two different terms are used for units of these two different raster data sets. Another thing is the value. What should be the value of pixel and cell in a grid? So the value is always, in case of image or in case of a pixel value, it is always positive integer value. So if I recall the discussion which we had related with our TIFF file, so typical TIFF file will always have values in whole numbers, in integers. If it is suppose a TIFF file is 8-bit file, then the values, the pixel values can be between 0 to 255. Maximum variations I can have only 256. And all values are whole numbers. So that is why we say positive integers. We cannot store in case of image any negative value or decimal or floating point values. So the values has to be the positive integer values only in case of image pixel. However, in case of grid, the cell value can be either positive or negative, and also can be either integer and real number. That means all kinds of values are possible. So if I go back to a slide here and about this digital elevation model or a grid. Now someone might be working in an area which is land part and sea part also, or beach area. So there I will have some positive values above mean sea level. I may have a surface below means below the water. So minus values also are required to be stored. But in case of image, all values will be positive values, because these values are not elevation values. These values are either either the reflecting or reflectance values, or can be emitted energy values. So these values cannot be in decimal. So that is major difference. And whenever you store in TIFF format, TIFF will force the cell pixel values to become integer value. So if you convert a grid to TIFF, you have to be very careful that the precision and the flexibility of for cell values which is available in case of grid is not available in case of image. And therefore, it makes further, though overall raster data is much easier to handle on either digital image processing or on GIS platform because of its simplicity, but image especially of one of the rasters is much more easier as compared to grid, because of only it handles only the positive integer values, and the life becomes much easier for processing person. So this is these two major differences are there between image and grid. Otherwise, concept wise both are two-dimensional metrics. And again, if these are mathematically two-dimensional metrics, so all tools for analysis of metrics which have been developed in mathematical domain through computer science, they have come into the GIS. So all these digital image processing and GIS raster data handling, all this has percolated into GIS, and therefore GIS is becoming further powerful. Any development which takes place in related with metrics, two-dimensional metrics, is beneficial in GIS also. Now this about I mentioned about the spatial resolution. So this is a common definition for image as well as for grid, that the measure of how closely pixels or cells can be resolved in an image. That means how I can identify different objects in two adjacent cells or pixels. And it depends on the basically properties of the system which is creating image or grid. Here, if two cells, in case of a grid, if two cells are having a large difference in the values, then they will come very distinctly. Whereas if they are having almost similar values, then you won't see. So this resolving things will not be, will be a different problem there. So higher the spatial resolution, when we say higher the spatial resolution, that means that we are talking very small size of the cell or pixel in comparison to ground area. If ground area by a cell or pixel is being covered very small, then we call as a high spatial resolution. For example, if a pixel is representing 1 meter 1 meter ground area, whereas in another image a pixel is representing 10 meter by 10 meter area, then I would in relative sense I would call the 1 meter is high spatial resolution and 10 meter is a coarse spatial resolution. Poor spatial resolution I should not call, because 10 meter, if I compare with 100 meter, then 10 meter is better. So relatively it is a coarser resolution if I compare with 1 meter. And higher the spatial resolution, I can distinguish different features, adjacent features more clearly. That means the resolving power improves, and it is only possible if I have the better spatial resolution data. So this is very important, because people talk about spatial resolution, especially nowadays when anybody who goes for buying a new mobile, always, earlier we used to have 5 megapixel camera, and then 12 mega, 15, 16, 18, now people are talking about 48 megapixels camera. So that means the number of rows and columns, if you multiply, that will come somewhere about 48 megapixels. So a one image taken by 48 megapixel camera would have these number of cells present there, or pixels present there. So higher spatial resolution sometimes may not be required for particular application. So it is not necessary that we should always go for higher and higher spatial resolution. It depends on our requirements. It depends on what kind of project I am doing. Because higher the spatial resolution, more the storage it will require and more the processing time it would require. Unnecessary it may occupy my hard disk space and even my RAM, though I do not require that high spatial. So optimization in spatial resolution must be thought before we employ a very high spatial resolution data. And that you can decide based on how, at what scale you are going to produce your results. For example, I may be using a 10 meter spatial resolution satellite image, but overall if I am going to create output on a A4 size for a district level analysis, then my scale in ultimate printout map is going to be very small. So why to use 10 meter spatial resolution data if I cannot show you to anyone? So optimization has to be always thought about this. For another way we say higher spatial resolution means more clear image, and this is how in case of image or grid. Now one another very interesting thing, may not be directly related with the GIS, but we sometimes handles that format also. I have already mentioned, that is about JPEG, and we will have a separate discussion about data compression where this JPEG reference will come again. Now JPEG is not a constructive image file format. That means it compromises on the quality of an image, however it provides better compression. However, there are various image compression tools which are available, which are non-destructive. Non-destructive means I can restore to original image quality, but JPEG is not. Now what people are committing mistakes, even they are buying a camera or mobile having 48 megapixel capabilities, but at the same time their image file is being stored in JPEG format. So you are employing a very high resolution camera, but at the same time you are destroying the image quality in order to save the space on your memory. So one has to be very careful. If you are really looking for very high quality images, change the option, store in TIFF, which is very common format. And there are compression tools available to compress your TIFF files which are non-destructive in character, and you can still compress it not to the level as JPEG provides, but you can anytime restore to the original image quality. But in case of JPEG, an image was acquired by a 48 megapixel camera, and originally it has been stored in JPEG. Now no image processing techniques can ever improve the quality of an image. So then this is very, very important here. Just to continue on this spatial resolution thing, I am having few examples and in two rows. On the right top right corner, we are having a spatial resolution of 30 meters, and you can see that the image is having people call as a pixelized or jagged image, and each cell or each pixel here is clearly visible, and it is relatively difficult to identify different objects which are present in this image. But if I move from 30-meter spatial resolution to more higher spatial resolution, that is 10 meter, now things have become quite interpretable. But if still my application requires much more higher resolution, I can also resort to a resolution which is 1 meter, and now things are really very clearly. So the resolving power is much higher in case of 1 meter as compared to 30 meter. Similarly, here again low resolution image, medium resolution image, high resolution. These are relative terms. So spatial resolution, whenever we talk about spatial resolution, we always talk about and talk in relative terms. Otherwise, none spatial resolution is the highest and none is the poorest. Because if I talk about remote sensing images, now even 30 centimeter spatial resolution satellite images are available. And the same time people are extensively using satellite images which are having 1 kilometer spatial resolution. So 1000 meter versus 0.3 meter. All for different applications, different spatial resolution data are employed. So optimization has to be there, a thinking is required before I employ that, though the data may be available to us a higher spatial resolution. But if my output does not require, why to employ? Why to use it? Use lower one, because ultimately I am going to produce in a say 50,000 scale. That does not require, because in that I will not have much details available or can show. So why to do it and then reduce the size? Now here for further discussion on this, sometimes you get the data in this kind of wordings: 1 arc second, or one third arc second, 1/9 arc second, 3 arc second, and what does it mean in terms of meters and other things. So what happens that a lot of digital elevation model data, DMs, are available in these terminology. So when they say 1 arc second, it basically means they are talking about roughly 30 meter. And when they say 3 arc seconds, then they are talking roughly about 3 arc second, they are talking about 90 meter. And how this arc second is coming? Basically, it is in terms of latitude, longitude. So because these the earth is a 3-dimensional body, so these are arcs, not like straight lines, though they are on maps, they are shown as arc. So that way also we should understand what is the meaning of 1 arc second or 3 arc second. Most of these digital elevation models are available in these terminology. They use this terminology: 1 arc second, 3 arc second, or 1/3 arc second, depending on what kind of data is available. So as you can see that when here this is the data in 1 arc second, one cell will represent this much ground area. But if I go for 1/3 arc second, then I am now having for the same area 9 cells. And if I go for 1/9th arc seconds, I am having many now cells to represent the same area. And the area here is maybe of like 1 arc second only, the 30 meter by 30 meter area. So likewise we should also, instead of simple meters, sometimes it is also denoted in arc seconds. Now in this later part of this discussion, I would like to spend some time on this comparison. Indirectly we have been comparing, but now we will have a complete dedicated discussion about the vector and raster data, how they are different, what are the advantages and disadvantages. As you can see, we have already discussed that vector is a discrete data and whereas raster is a continuous data models. So that is one major difference is there. And GIS, the good GIS softwares are capable of handling vector, raster and TIN, and of course non-spatial data as well. So there is no issue about the data, but GIS handles all these three data sets completely differently. But currently we are going to discuss vector versus raster. And now TIN is also considered as continuous as raster, but the concept wise different. So if a real world has to be represented in these two different models, one is raster, another one is vector, how it would be represented. So real world, depending on the scale, like house here in the vector data is represented as a point. A stream, river, though it is having width in real world, but at this particular scale it is represented as a polyline which you can see here. And a forest like here, which is shown in form of tree, is represented in form of polygon, and same with this. So all three vector entities can be used to represent the real world. And of course, once we model the things from real world to vector, this is discrete and this is abstract reality. Like river which has the so smooth curves and width, all have gone except some lines. So it is a reduced version of the real world, abstract version of the real world. If I have to represent the same real world into the raster through raster model, then the representation is going to be completely different. For example, here for the house, now this house is occupying an area, because if say resolution is 1 meter by 1 meter or 2 meter by 2 meter, then I am 2 meter resolution, then this house is being represented as a 4 square meter area. But as for definition of vector, point is 0 dimensional entity. But this cell in this grid may not be representing the true area of the house, the constructed part of the house. So that means here also this is not true representation of the real world. In earlier discussion I have already mentioned, which I am going to repeat, real world is really real in 1:1 scale, and which is cannot be represented by any models in true fashion. Whatever the models which we are using are stripped version of the reality, abstract version of reality, and therefore errors will keep coming, will come in our data. So like comparing a point, a house being represented as a point data, 0 dimensional entity in vector, whereas in raster a cell will occupy some space. Similarly, if I compare the this stream, river, then here it is being represented, but not as smoothly even in case of vector, and it is completely in stair steps case or jagged representation. And same with my forest, like here this forest is here it looks little smoother, but here it is just 3 cells which are representing the one. So if I am having relatively coarse resolution data, my error component representing the real world would be very large. But if I go for very high spatial resolution data in relative sense, then my error component in terms of area and the quality, my error is going to be less. That is also true in case of high spatial resolution data. But if it is required, then only, and if that margin is available for errors, it is fine to even use medium resolution or coarse resolution data. So real world can be represented in 3 different spatial models: vector, raster, and of course later on in future lectures we will be also discussing 10. You can see here that vector is a discrete, and like in this area you do not have any information. Though in real world there is a land, that may be agricultural land, waste land or any other, but there is a land. But in case of raster, each cell will have some value, and that is why it is a continuous, no gap in the data. One cell ends, another starts. One pixel ends, another starts. No gap in between. So in vector data model, information about point lines and polygons is encoded and stored as a collection of xy coordinates. So for a point you are having just one single pair x and y. For a polyline you will have many, and same with the polygon. And vector model is extremely useful describing discrete features, but relatively less useful for describing continuous. So if I have to describe a soil type, as you know in nature and the soils will not have a very sharp boundary, and therefore if I want to use that soil type layer or theme, then it is better to represent the soil map through a continuous model, that is raster, rather than vector. So it depends on what kind of data I am going to handle, what kind of theme I am going to handle. A raster model has evolved to model such continuous features. Terrain, another one is if I want to represent topography of a hilly terrain like part of Himalaya. Then in vector I will be using contours, and it is not very easy, and therefore in order to represent terrain, variations of undulations and ruggedness, then the best model to represent either tin or raster. And both models, that means vector and raster, are having merits and demerits, that means they are having unique advantages and disadvantages. And all these models, including your tin, can be handled with all modern GIS softwares. So very quickly we will go through these advantages and disadvantages. Like vector advantages, that it is position wise, it is quite accurate representation. But in case of raster, that kind of accuracy may not be available. You have seen in case of a house or a forest or a river stream or whatever. So accurate positional information, if one is required, then go for vector representation. Of course, vector does not require much space. Memory requirements are very little compared to raster. So therefore it is compact, processing is compact also. And probably you do not require any compression techniques because there will not be any redundancy. Redundancy means unnecessary space it will not occupy on your hard disk. So redundancy is not present at all in vector, and especially if you have built up a topology, then the quality of vector data is going to be very high without any redundancy, and you do not require compression tools either. That is why there is hardly any development of compression techniques for vector data. And vector data you can associate n number of, theoretically n number of, unlimited number of attributes, whether say point, line or polygon. Each point can have hundreds of attributes. I showed example of those Himachal Pradesh hydro potential sites. I had about 20 attributes associated with each point data. But in case of raster, only one attribute is possible. That is the biggest limitation. So far, this is what it has been developed. Maybe in future we do not know. But in different layers you can have for the same. So one layer, raster layer you are having for elevation, another one you are having for pollution, third one is you are having for depth or any other thing. You can still have multiple attributes, but through different layers. But in case of vector, you can have in single layer you can have n number of attributes theoretically. Since raster is based on two-dimensional matrix concepts and processing, therefore mathematical and overlay operations are very easy compared to vector data. I would be showing an example where vector will find a limitation, but raster does not have a limitation over overlay operations. And other is the satellite information is easily incorporated, because if I am using grid, I want to also use satellite data, both are raster, no issue, very compatibility is there. But if I am using vector data and I want to use satellite images, then I may not have that kind of compatibility. So, for any kind of continuous phenomena, one should always resort to the raster rather than vector. Further one discussion about the comparison of these two, raster versus vector. Raster divides data into grid cells, vector uses point lines and polygons, and processing can be done in grid cell or converted to vector format. That means the conversion from one format to another is also possible, but it is not fully transparent. That means if you convert from raster to vector, you will introduce some errors, and if you convert from vector to raster, again you will introduce, because both models conceptually are completely different. I will discuss little bit about how you can convert from one format to one model to another model. So, the processing part is quite fast in case of raster if it is not very big data set or a 2-day array, and easy integration with remote sensing data. Modern GIS, they all allow and support handling of raster and vector data. This conversion is quite limited, and like raster to vector conversion is not fully automatic yet. It is still semi-automatic, or you can call as a manual, and but vector to raster automatically it can be done. Raster is simplest to store in the computer. Point is represented by a single cell, as you know, and a line representing by a group of neighboring cells, and set up as rows and columns in case of raster, and each cell pixel is assigned a value. So, unit in case of vector can be point, line, polygon, but ultimate is the coordinate x and y pair. But in case of grid or raster, you are having either cell or pixel as a unit. High spatial resolution, smaller cells representing a smaller ground area will require more space to store and more processing time. Now, from a visible quality point of view, how boundaries are represented better in which model. So, if I see a vector map, then I find that the boundaries are very well represented by a map through vector representation. But if the same map has to be represented in this raster format, then this is how. So, the problem you would notice that major problem is all along your boundary line. Your boundaries are not as smooth or clean as in case of your vector data, because vector is capable of representing very accurately the boundaries, whereas raster will have a jagged kind of issues here. So, the boundaries are a stair-step case or a jagged thing is there, boundaries are not smooth. However, if we improve the spatial resolution or get high spatial resolution data, then this much of error you would not notice. So, in a complete comparison through a table, we will go one by one. These are the characteristics: vector data structure, raster data structure, and in summary, raster data structure is if we go, raster data structure is simple compared to that vector is complex. If I have to learn, then of course raster is simpler, because it is just 2-dimensional matrix, a 2D array, whereas our vector sometimes is difficult, and softwares are also complex in that case. If I talk about positional accuracy, then more precision and accurate is the vector data, whereas precision increased only if I increase the spatial resolution in case of raster. And attribute precision, again there are a lot of attributes I can store, and attribute precision in case of vector is relatively higher than what you are having in case of raster. Now, comprehensiveness of analysis capabilities, good for a spatial query. I showed how to build a query, a simple or nested query on a point data or any other vector data, and you can do it quite easily. However, if I have to do the query on spatial data, it is not that good capability currently of GIS software. So, that is one of the limitations of raster data. Now, if I go for overlay ability, then vector will provide overlay ability quite good, but up to certain layers. And if you increase number of layers in overlay analysis like A union B union C D, then your output would become very complicated. But in case of raster, all pixels or cells are lined up, though they may have different spatial resolutions, but still overlay can be performed on tens of 20 raster layers in one go. So, that is very big advantage with raster data structure. Storage requirements we have already discussed. The vector requires small but complex. Complex means here many files will be created, as we have seen while discussing the topology. But in case of raster, sometimes even a single file will store the entire raster layer without any problem. Why I said sometimes? Because sometimes there may be only one layer or one data like .tif file, or sometimes you also have the compression information and other things. So, two more files might be there. So, that is why I said that number of files in case of raster on a computer system against one layer are going to be less as compared to the vector. Now, ability to work with image data. Of course, raster is image is part of the raster, one type of raster. So, fully compatible with raster, but in case of vector it is very poor. Conversion to other map projections, because as you know that each country is having their own map projection, and because everyone would like to represent their country in a true shape and size. So, there are hundreds of such projections have been implemented into the GIS, but all of them are not fully transparent again. So, if I have to convert my data from one projection to another, especially the vector data, then it is generally it is quite smooth and I can do it very easily. Most of the GIS software will provide tools to convert from one map projection to another. But in case of raster, it is having a little difficulty to convert from one format to another, because their boundary areas, margins will have a big problems there. Now, the another characteristics to ability to work with network data structures. Raster is very poor because it is a continuous data, whereas a vector is good because like a stream network or power grid network, it is very good. Remember also the first GIS software was also developed for handling network data, and therefore since 1960s, early 60s till today, lot of development has taken place on this front. So, most of the GIS softwares are very good to handle the network data, though handling that data, preparing that data for network analysis may be little challenging and difficult. But once you have developed a layer which is having complete network built up, then there will not be an issue, because there might be a direction, flow direction may be in two direction or single direction. Like in case of natural drainage system, a stream network will have only one direction flow, and therefore developing such a network and analyzing flow conditions or pollutant flow through these networks is easier. But if it is a two-way flow like in road or other systems, then there may be challenges there. But accordingly the systems are developed. If we bring the cost expensive and really very expensive compared to raster data. Nowadays lot of satellite images, digital elevation models, both are rasters, are available almost free of cost on net. but hardly vector data is available free, because it has to be created. You cannot do it like satellite images, which are acquired almost automatically by the satellite sensors. And then using those images, you analyze, like you develop a vegetation map or forest cover map, or for you use for agriculture or for in earth sciences, geology. And you can also develop digital elevation models. So, many digital elevation models have employed different remote sensing data sets, and therefore, only the processing is there, but data becomes inexpensive. But in case of vector, each point, line, polygon has to be digitized. That is why it is expensive. If we consider output map quality, then of course the vector is very good, whereas raster is poor from map quality point of view. Poor only when it depends again on scale and depends also on the spatial resolution. If raster data in relatively high spatial resolution, that may not be that poor. And if you are high spatial resolution, you are representing in a map which is say in A4 size or 50,000 scale or so, then that may not be poor either. So, this output map quality is also very important. Now, I mentioned about this overlayability. So, we will spend few more minutes on this part, and that is a very simple example here is taken. I am having one map which is soil map, another one is land use map, and both these maps are having only 3 polygons each. Now, when I overlay, and then I may end up with 9 polygons or more or less, depending how they intersect with each other. And therefore, not only the number of columns in my attribute table will increase, but number of polygons have also increased in my map, which you can see here, which is soil land use map. But the GIS are capable to handle these overlays of vector data up to certain extent. But if you go and overlay 10, 20 or even 5 maps like this, each is having 3-4 units in it, then you would end up with 30-40 polygons of smaller and smaller size. And the usage or interpretation of such maps would be very difficult. Theoretically, practically you can overlay, but output we have to understand. That is the thing in GIS, whatever the advanced analysis you perform, but whatever the output would come, we have to understand, we have to explain. And the best thing, as I told also in the demonstration, do it in a step manner. Maybe 2-3 maps, first you overlay, create an output. If I have to do it say for 6, 3 in one go, 3 in one go, and later on these 2 outputs of 3 I can overlay, and so I will have understanding in a step manner. So, here if I take this example, here units are numbered for our simplicity, they have been kept ABC. Here they have been kept as 1, 2, 3 as ID of these polygons, and when I overlay, then now there is A2, A3, B3, B2, something like this. So, here in my output table, A2 is agriculture in my land use map. So, A is agriculture in my map, which is A2. So, 2 is here, and A is having depth, soil depth is 50 centimeter, 150 centimeter. So, likewise, if I take the say C3, so C is having depth of 90 meter, and 3 means pasture. So, C3 pasture 90 centimeter. So, likewise, a table can be developed or developed by the software or can be developed by ourselves, and overlay to certain extent of vector data is possible. But if I have to do it for 20-30 layers having all in vector, then it would be very difficult. But if I do it using raster data, it is not that difficult. Still, output from both models you have to understand and use that one. So, last here is the conversion, vector to raster conversion and raster to vector conversion. As I mentioned earlier, it is possible to convert from one format to another or one model to another. But always when you convert from one to another, because these conversions are not fully transparent and therefore they will introduce errors. So here if I have to convert from vector to raster, the first one, then what I am determining? I am determining the row, the column and row number. So L here is the scan line or row number, E is the pixel or E or the element pixel number. That is the location, not the value. Now here there is a function. So these are my polynomial functions, because input is I am having, in case of vector to raster conversion, I am having input x and y, my coordinates. So for row and column I will have the same equation and similar polygon functions, polynomial functions. In case of raster to vector, again I will be employing different polynomial functions, but here I am going to determine coordinates using input as row number and column number, L and E. So L stands, as I have said, scan line or row in raster, E is the element, the pixel or column number, X is the horizontal coordinate, Y is the vertical coordinate, and so on. And the value, if it is from vector to raster, like first one, what would be the value of the cell is a separate issue. This is only conversion from there. The value has to be assigned also, and that is why, because these two models are conceptually completely different. Even then we are trying to convert from one format to another, we are bound to have errors in it. So one has to be very careful. Again the same point I can bring, that whenever you are doing one conversion from one to another, do not delete original file, especially the vector file, because vector data is very expensive. So keep the original file and you can have another file which is converted to raster, and same with vector to raster and raster to vector. So this one has to remember very carefully, because once I have converted from vector to raster and the same time I have deleted my original vector file, tomorrow I require my original vector file, I cannot restore by any means whatsoever. No processing tool you would find in any software which can bring you the original vector file, except if you get the backup from somewhere. So these are the very important point here. Examples are also here. The same this network which we are seeing, if I convert into raster, this is how it would be visible. But if I zoom it further, then I will start seeing that jagged or stair steps case in case of raster, but not in vector. So there is always a conversion issues from one to another. Another for point data, if I convert point to raster, something like this will happen. If I convert line to line features to the raster line features, again I will have these jagged issue or stair steps case issue. And if I am converting from polygon to raster polygon, basically raster, I am having the boundary problems and spatial resolution problems with raster data. So both models, raster and vector, are having various advantages and disadvantages. This is the last image just to understand in a much better manner, because everyone is having a child in him, and therefore whenever we see cartoons it becomes automatically attractive. So the same thing I am going to explain through that if you see that in vector it looks very smooth, very clean, but in case of the same cartoon is being represented here which is not as clean. If I improve the spatial resolution of this raster image, I can have better representation, but that would not be close to my original vector file. So if I convert from vector to raster, this is what I am going to end up. And therefore the vector file should not be deleted without much thinking. Make sure that you are having backup, because it does not require much space, memory. So, do not unnecessarily delete vector files, because it is not easy to create. So, problems I have already mentioned. So, very briefly we will go. So, whenever you convert from one format to another, there will be degradation of the quality of data. Many examples I have shown, and the issues includes like loss of details and loss of accuracy, and stair steps case in case from vector raster to vector, and changes to the original data, and so on and so forth. Now, which model to choose? Of course, it depends. The best answer to this question is that it depends on your project. Also depends what is available. If a raster is available, my project is also requires raster data, then why I should bother about vector data? And same with vector. But sometimes we have to do it this kind. So, we know raster is faster, but vector is correcter. Means it is having a more correctness, more accurate representation. So, raster is useful when working with continuous data types, for example, elevation, slopes, satellite images and so on. Good for large area analysis, good for surface analysis, because a raster by nature is representing a surface. That surface may be elevation surface, that may be a pollutant surface, soil surface and so on. And mathematical modeling, because it is a 2D or 2-dimensional array, so all those modelings and other things are easy to perform. Spatial details, if they are not important, then is fine. Vector data is useful when working with discrete data types like tree, buildings, property boundaries and etc. If somebody is working say in revenue department, then raster is not good. The vector, because accuracy is very much required there, and you are representing various boundaries or land records very in form of polygons, then vector is good. And good for a small study areas. If a study area is large like continental scale, then vector is not good. Spatial details is important. When close enough, it is really not good. That means that if I am working for a terrain like Himalaya and I am using the vector data, that means my contours would be so close to each other that sometimes it is very bad from analysis point of view. So, they become so close because the ruggedness, the slope is very high, but in case of raster that difficulty will not be noticed. And finally, here that when topology is needed for the analysis. In case of raster, you do not have to bother about topology, but in case of vector, of course, topology is always required, especially for the polygon data. And other factors which can influence your decision, which includes the available storage, because raster requires a really large storage space. Expected types of analysis, some tools only work with raster or vector data, and expertise of human operators is also required, level of accuracy desired, that will make our decisions. And some examples are here with the ArcMap GIS software converting from vector to raster. So, there are tools available, you can convert raster to polygon, raster to point, contours, streamlines, features, raster to polygon, and when you have to calculate cost part and other things, then it is always go for vector. Raster to polygon also required when we are working for view set, water set analysis. Raster to polygon is also required elsewhere. Now, point to raster data, that is means creating from discrete to continuous, and the tool is available for us is interpolation tools. And these tools, interpolation tool includes various interpolation techniques, for example, kriging, very popular one, inverse distance weightage method, SP-line and many more, and variants of these tools are also available. And not only in this particular software, but many softwares are there. Density tools are also available, because point data density analysis is required in many applications. point to raster, polygon to raster, you convert raster domain and polygon to raster. So, point to raster, polyline to raster and polygon to raster, all these things sometimes for certain types of analysis we require. And like topo to raster means here the topography or topographic map, but there is no automatic conversion is available from raster to vector. This one has to remember. So, with this we come to end of this discussion. Thank you very much.